Imagine the universe going completely dark. Not the darkness of a moonless night, not the murky black of a deep cave. Total darkness, the kind that would exist if every star were snuffed out at once, if every atom stopped vibrating, if the electromagnetic field that threads itself through every corner of existence simply went silent. Nothing to see, nothing to feel, no warmth reaching skin, no color pressing against the back of the eye. Silence so absolute it wouldn't just feel like blindness. It would feel like the end of all sensation itself. That darkness is the universe without photons. And understanding exactly what a photon is, not what it does, not what it looks like, but what it fundamentally, irreducibly is, turns out to be one of the deepest questions physics has ever dared to ask. If this kind of deep dive into the fabric of reality excites you, it would mean the world to us if you liked this video and subscribed. It helps us keep making these explorations. The word photon is everywhere. It appears on sunscreen labels and fiber optic brochures and quantum computing press releases. People say it casually, as if they know what it is, as if the word itself is self-explanatory. But ask someone to describe what a photon actually is. Not what it does, but what it is. And you will watch the confidence drain from their face. Most people, if they're honest, picture something like a tiny speck of light, a glowing grain of something drifting through space the way a mote of dust drifts through a sunbeam. Something small, something bright, something essentially particle-like. A little nugget of luminosity bouncing from point to point. That picture is not even close. And the gap between that intuitive image and the truth of what a photon actually is happens to be one of the most revealing gaps in all of human understanding. Crossing that gap requires you to abandon almost everything your senses have trained you to believe about the nature of matter, space, and reality itself. It requires stepping into a world where the familiar categories of wave and particle dissolve, where fields are more fundamental than objects, where a thing can have momentum without having any mass at all, and where the very concept of standing still becomes physically forbidden for a certain class of entity. That forbidden stillness, that compulsory eternal motion, is not a quirk or a curiosity. It is a window into the geometric soul of the universe. To understand why the photon is what it is, you have to trace the long and often humbling history of how human beings first tried to make sense of light. The story begins not in a laboratory, but in the ancient world, in the minds of thinkers who had no instruments, no controlled experiments, and nothing but observation, intuition, and argument to guide them. And remarkably, some of those ancient arguments were stranger and more creative than anything most people encounter in a modern physics classroom. The early Greeks were obsessed with vision. They watched light cast shadows with geometric precision. They watched it reflect off still water. They watched it bend when it entered a pool. And they asked, with genuine urgency, what is happening? What is the relationship between the eye, the light, and the thing being seen? The answers they offered were dramatically different from one another. Some philosophers argued that the eye was not a passive receiver, but an active emitter, that something radiated outward from the pupil, reached out and touched objects, and returned with their form intact. It sounds bizarre today, but there was a certain poetic logic to it. When you look at something, you feel as if you are reaching toward it with your gaze. The idea of emanation from the eye captured that felt sense of directed attention. Other thinkers rejected this and argued the opposite. That light was something that existed in the medium between objects and observers, a kind of quality or disturbance in the transparent substance of air. On this view, light did not travel from anywhere to anywhere. It simply modified the conditions of the space between a source and an eye, like the way heat distributes itself through a room without any particular thing carrying it. Neither account was correct, but both contained a seed of something real. The debate about whether light was something that traveled outward or something that was more like a property of space would echo, in far more sophisticated forms, across the next 2,000 years. The first genuine breakthrough came when careful observers started measuring, not just watching light, but forcing it through apertures, reflecting it off curved surfaces, refracting it through shaped glass, and recording what happened. By the 17th century, the behavior of light had been cataloged in enough detail that theorists could no longer get away with vague descriptions. They needed precise mechanical models, and two towering figures of the era built precisely that, one arguing for particles, one arguing for waves, and planted a controversy so deep it would not be resolved for 3 centuries. Isaac Newton was the particle man. He had good reasons. Light travels in straight lines with the kind of mathematical precision that particles moving through space would naturally exhibit. Reflections obey the same law as billiard balls bouncing off a wall. When Newton used glass prisms to split sunlight, he showed that white light was composed of many different colors, each bending at a different angle when passing through glass, as if each color were a different type of corpuscle with a slightly different interaction with the medium. His theory was elegant, mechanistic, and fitted neatly inside his broader vision of a universe made of matter in motion. If everything else was particles obeying mathematical laws, why should light be any different? Christian Huygens saw it differently. Huygens had watched light bend around the edges of objects in ways that particles simply did not do. He had watched it spread when forced through a narrow opening, fanning outward in a pattern that reminded him far more of ripples on a pond than of bullets flying through a gap in a fence. Waves bend, waves spread. Waves do the things light does around corners and edges. Huygens proposed that light was a wave propagating through a medium that filled all space, a medium he called the ether, and his wave model explained diffraction naturally and beautifully. The argument between these two frameworks dragged on, but Newton's reputation was so enormous that the particle view dominated for most of the following century. Then, in the early 1800s, a series of experiments tipped the scales so dramatically that the particle theory appeared to be finished. Thomas Young shone light through 2 narrow slits in a barrier and looked at what appeared on a screen placed behind them. If light were particles, the result should have been straightforward. 2 bright bands on the screen, one behind each slit, like 2 streams of tiny bullets passing through 2 gaps. But that was not what Young saw. Instead, the screen showed a pattern of many alternating bright and dark bands, a zebra stripe of light and shadow that had no business being there if particles were responsible. The dark bands were the key. Where particles would have simply accumulated and made the screen bright, the light was completely absent. 2 beams of light, overlapping, had conspired to produce darkness. The only mechanism that could do this was interference, the cancellation of peaks by troughs, waves destroying each other when they were out of phase. Light was behaving exactly as water waves behave when 2 sets of ripples cross paths and cancel. The conclusion was inescapable. Light was a wave. The particle theory was dead, or so it seemed. By the middle of the 19th century, waves had won so completely that the only remaining debate was about what exactly the waves were vibrations of. Sound waves are vibrations in air. Waves on water are vibrations in the water. Every wave physicists had ever studied vibrated in some medium. So, what was light vibrating in? The ether hypothesis was resurrected, an invisible, all-pervasive substance that filled space and served as the medium for light's oscillations. The ether had to be extraordinarily rigid to support the high frequencies of visible light, yet perfectly permeable to all matter, since Earth moved through it without any apparent resistance. These requirements were deeply uncomfortable, but no one had a better answer. Then James Clerk Maxwell arrived and changed everything. Maxwell was not trying to explain light when he began his work on electricity and magnetism. He was trying to understand why electric fields and magnetic fields behaved the way they did, why a moving charge produced a magnetic effect, why a changing magnetic field could drive a current in a wire. He built a set of equations to describe these relationships, and when he solved them, he found that changes in the electric field and changes in the magnetic field fed into each other in a cyclical way. An oscillating electric field would generate an oscillating magnetic field, which would generate a new oscillating electric field, which would propagate outward through space. He calculated the speed of this propagating disturbance using purely electrical and magnetic constants that had been measured in labs, numbers that had nothing to do with light. The speed came out to approximately 300,000 kilometers per second. It matched the measured speed of light to astonishing precision. Maxwell understood immediately that this was not a coincidence. Light was not something separate from electricity and magnetism. Light was electricity and magnetism in motion. It was an electromagnetic wave, a self-sustaining oscillation of electric and magnetic fields, each one regenerating the other as the disturbance traveled forward through space at a speed determined by the properties of the electromagnetic field itself. This was one of the greatest acts of intellectual unification in history. 3 phenomena that had seemed completely unrelated, light, electricity, and magnetism, were revealed to be three faces of the same underlying reality. And Maxwell's equations had something else remarkable about them. They didn't require an ether. The electromagnetic field did not need a medium to wave in. The field itself was the thing. The electric and magnetic components existed in space as real physical entities, and they could oscillate and propagate on their own authority. When Albert Michelson and Edward Morley attempted to detect the ether in 1887, by measuring whether light moved at different speeds in different directions, as Earth plowed through it, they found nothing. No speed difference. No ether. Light moved at exactly the same speed in every direction, regardless of Earth's velocity. The ether did not exist. The field was its own medium, and it filled all of space not as a mechanical substrate, but as something genuinely novel, an entity in its own right, invisible and intangible and perfectly real. So, the 19th century ended with a tidy picture. Light was an electromagnetic wave, perfectly described by Maxwell's equations, requiring no medium, traveling at a fixed speed through the vacuum of space. Case sealed. Physics could move on, except that two experimental results refused to be sealed away, and each one contained a crack that would eventually split the entire framework open. The first crack was the photoelectric effect. Certain metals, when illuminated with light, shed electrons from their surfaces. This had been known since 1887. The wave picture seemed capable of explaining it. The electromagnetic wave arrives. Its oscillating electric field shakes the electrons in the metal, and if it shakes them hard enough, they escape. But the details were relentlessly wrong. The wave model predicted that dimmer light would simply take longer to liberate electrons, because a weaker wave would need more time to transfer enough energy to push one over the escape threshold. In practice, no delay was observed. Even the faintest light of the right color produced electrons immediately, the instant it arrived. Intensity affected how many electrons were released, but not when the first ones escaped. More critically, the energy carried by each individual ejected electron depended entirely on the color of the light, its frequency, not on how bright the light was. Flooding the metal with intense red light did nothing if the frequency was below a certain threshold. A feeble trickle of ultraviolet light, higher in frequency, would knock electrons loose immediately. Turning up the red light's intensity just released 0 electrons faster. The threshold was about frequency, and the wave model had no way to explain a frequency-dependent threshold. Waves carry energy in proportion to their amplitude, their intensity, not their frequency. If light were purely a wave, there should be no threshold at all, just a matter of time before enough energy accumulated. In 1905, a young patent clerk in Bern named Albert Einstein looked at this anomaly and proposed something that the physics community was not ready to hear. He suggested that light did not deliver its energy in a continuous stream, like water from a faucet. Instead, it delivered energy in discrete packets, individual, indivisible chunks, each carrying an amount of energy directly proportional to the light's frequency. The constant of proportionality was a tiny fundamental number that had already appeared in the work of Max Planck, who had used it 5 years earlier to solve a separate mystery involving the colors emitted by hot objects. Einstein was proposing that these packets were not just a mathematical convenience. They were real. Light was, at some fundamental level, granular. It came in pieces. Each piece of light could knock out at most 1 electron, transferring all of its energy in one instantaneous event. If the piece carried enough energy, meaning the frequency was high enough, the electron escaped. If not, nothing happened, no matter how many pieces arrived. This explained everything. The threshold, the independence of electron energy from intensity, the 0 delay. It was a complete and clean explanation. Einstein's proposal met resistance because it seemed to contradict everything wave optics had established. Interference, diffraction, polarization. All of this evidence for wave behavior would have to coexist somehow with this new evidence for particle behavior. How could light be both? The physics community spent years trying to find a way around Einstein's explanation, trying to preserve the purity of wave theory. Eventually, the experimental evidence became impossible to deny. In 1921, Einstein received the Nobel Prize in Physics, not for relativity, but for this explanation of the photoelectric effect. light came in packets. These packets were named photons in 1926, and the question then became the same question we are still asking. What exactly is a photon? The instinctive answer, the answer that most people reach for, is that a photon is a tiny particle of light, a microscopic bullet, a diminutive corpuscle in the spirit of Newton's original proposal, updated with quantum mechanics. This answer feels satisfying. It is also deeply inadequate because it misses what a photon actually is at the level where physics becomes strange and beautiful and genuinely surprising. To reach that level, you need to think carefully about the electromagnetic field, not as an abstraction, not as a tool for calculating forces, but as a real physical thing. The electromagnetic field exists everywhere in the universe simultaneously. At every point in space, at every moment in time, there is an electromagnetic field. Right now, where you are, electromagnetic fields are passing through your body, radio signals from distant transmitters, infrared radiation from every warm surface around you, the faint microwave glow of the cosmic background left over from the early universe, visible light scattering off everything in your environment. The field is always there. When no light source is present, the field is in what physicists call its ground state, the quietest it can be, but it is never absent. It permeates everything, always. Think of an ocean. The ocean exists whether there are waves on it or not. The water is there, filling the basin, extending to the horizon, whether the surface is glassy calm or storm-churned into chaos. A wave is not a separate thing from the ocean. A wave is the ocean's surface doing something, rising and falling in a pattern that propagates. You would not say a wave is made of some different substance from water. A wave is water, but water in a state of organized motion. When the wave passes, the water is still there. The wave has not brought extra water with it and left it behind. The water was always there. The wave was simply the field expressing itself. The electromagnetic field is like that ocean. It fills all of space. A photon is like a wave on that ocean, not a foreign object dropped into it, not a speck of something floating on the surface, but the field itself in a state of excitation, a region of the field that is vibrating. The photon is not in the field. The photon is the field, locally and temporarily disturbed. But this analogy breaks down in exactly one place, and that breaking point is what makes quantum mechanics quantum mechanics. Ocean waves can come in any size. You can make a tiny ripple with the tip of your finger, or you can make a monstrous swell with a hurricane. The energy of a wave is continuous. You can add as much or as little as you want, in arbitrarily small increments. The electromagnetic field does not work this way. The energy of the electromagnetic field at any given frequency is not continuous. It comes in discrete steps. You cannot have half a unit of electromagnetic energy at a given frequency. You cannot have 1 1/4 units. You get whole numbers, 1 unit, 2 units, 3 units, and nothing in between. This discreteness, this refusal of the field to accept fractional amounts of energy, is the essence of quantization. Each minimum indivisible unit of electromagnetic energy at a given frequency is what we call a photon. The photon is not a particle sitting inside the field the way a raisin sits in bread. The photon is the field in its first level of excitation above the ground state. It is the smallest possible disturbance the electromagnetic field can sustain. You cannot split a photon in two and get half a photon. The field simply does not have a half excitation state. There is 0 excitation, and there is 1 excitation, and the gap between them is the photon. This understanding has a consequence that is hard to overstate. When you ask what a photon is made of, you are asking the wrong kind of question. The question assumes that photons are composed of parts, assembled from smaller ingredients, constructed like ordinary objects. But a photon has no internal structure. It is not built from subcomponents. Physics has probed the photon with the most powerful experimental tools ever devised. Particle accelerators that can resolve structures 1,000 times smaller than a proton. Precision measurements that can detect effects at the level of parts per trillion. And no internal structure has ever been found. A photon is not like a proton, which turns out to have quarks and gluons churning inside it, a seething internal ecosystem of subnuclear particles held together by the strong force. A photon is not like an atom, which has electrons orbiting a nucleus. It has nothing inside it. There is no inside. There are no subcomponents. There is no hidden machinery determining its properties. The properties a photon has, its energy, its momentum, its polarization, the direction it travels, are not stored inside it like data on a chip. They are properties of the electromagnetic field's state of excitation. They describe how the field is oscillating, not what the photon contains. The energy of a photon is entirely determined by the frequency of the field oscillation, how rapidly the electric and magnetic fields are cycling. Through a relationship so clean, it seems almost too simple. Energy equals a fundamental constant times the frequency. This constant, Planck's constant, is one of the most important numbers in nature, appearing wherever quantum mechanics touches physical reality. It sets the scale of quantization. It is the size of the irreducible grain in the fabric of energy. A red photon, produced when an electron in a neon atom drops between energy levels, carries a specific amount of energy determined by the frequency at which those atoms' characteristic oscillations happens to fall. A gamma-ray photon, emitted when an atomic nucleus sheds excess energy, oscillates at millions of times the frequency and carries millions of times more energy. An infrared photon from the warmth of a human hand carries far less. But in every case, the energy is entirely a function of the frequency. There are no other variables. There is no knob to turn that adjusts the energy independently of the frequency. The two are permanently, inextricably linked by Planck's constant. Change the frequency and you change the energy. Want a more energetic photon? You need a higher frequency oscillation of the field. There is no other way. Now consider the question of size. People naturally want to know how big a photon is. The desire to assign a spatial extent to something that seems particle-like is almost irresistible. The answer, the standard model of particle physics gives, is that the photon is a point particle. It has no spatial extent, no radius, no volume in the classical sense. This is not a dodge. The concept of size as we apply it to ordinary objects, the radius of a marble, the length of a pencil, applies to things that have extent because they have internal parts that occupy space. A proton has a size, roughly a femtometer, because it has quarks inside it that are separated by distances on that scale. The boundary of a proton is the boundary of the region its constituents occupy. But a photon has no constituents. It has no boundary between an inside and an outside. Asking for the size of a photon is like asking for the color of an abstract concept. The question does not have an answer because the concept it is asking about does not apply. What a photon does have is a wavelength. The wavelength is not the photon's size. It is a property of the field's oscillation pattern, the spatial distance between one cycle and the next, as the electromagnetic wave propagates. A radio photon has a wavelength of meters or kilometers, the distance between successive peaks of the electromagnetic oscillation as it moves through space. A visible light photon has a wavelength of a few hundred nanometers, a fraction of a thousandth of a millimeter. A gamma-ray photon has a wavelength smaller than a single atomic nucleus. These wavelengths determine how the photon interacts with structures of different sizes. A radio photon passes right through a concrete wall because the wall structure is far smaller than the photon's wavelength, while an ultraviolet photon can ionize molecules because its wavelength is comparable to molecular scales. But the wavelength is not a description of the photon's physical extent. It is a description of the field's oscillation rhythm. The question of a photon's position is even stranger. Quantum mechanics adds a layer of fundamental indefiniteness to the location of any particle, and for the photon, this indefiniteness is especially deep. In quantum mechanics, the more precisely you try to confine a particle to a small region of space, the more wildly its momentum, and hence its energy, fluctuates. For photons, this becomes particularly acute because their energy is tied directly to their frequency. And their frequency is tied directly to what it means for them to be a specific photon at all. A photon confined so tightly that its position is sharply defined would have such a broad spread of energies that the concept of a single photon with a definite frequency would dissolve. Some physicists argue that a rigorously defined position operator for photons does not even exist in the same mathematical sense that it does for massive particles. The photon is best understood not as a little object located somewhere in space, but as a quantum state of the electromagnetic field, a state with definite energy and momentum propagating through the universe, but without a single definite location until the moment it is absorbed. This leads naturally into something that generations of physics textbooks have handled clumsily: the so-called wave-particle duality. The story that is usually told goes like this. Light sometimes behaves like a wave, as in diffraction and interference, and sometimes like a particle, as in the photoelectric effect, and this dual nature is a fundamental mystery of quantum mechanics. The photon seems to switch identities depending on which experiment you perform. This narrative, while not exactly wrong, is misleading in a way that actually prevents deeper understanding. It suggests that the photon is secretly two things and performs a switch based on some secret knowledge of what is being measured. That is not what is happening. The photon is always exactly one thing: a quantum excitation of the electromagnetic field. This one thing has wave-like properties because the electromagnetic field is a field, and fields oscillate, and oscillations produce interference and diffraction. It also has particle-like properties because its energy is delivered in an indivisible quantum. When it is absorbed, the entire energy arrives at one place in one instantaneous event. Both behaviors arise from the same single reality. The wave is the field. The particle is the quantum. The photon is a quantum of a wave field, and neither face of this identity contradicts the other. They are two aspects of a more fundamental thing that has no perfect classical analogy because nothing in everyday life is a quantum field excitation. Our language has words for waves and words for particles because we evolved surrounded by water and rocks and birds. We did not evolve surrounded by quantized fields, so we have no inherited vocabulary for what a photon actually is. The apparent duality is a limitation of our language, not a property of the photon. The framework that handles all of this correctly, that explains both the wave behavior and the quantum behavior, that describes how photons are created and destroyed, that connects the photon to the forces of nature, is quantum field theory. This is not a popular science concept. It is not a metaphor. It is a precise mathematical framework that represents our deepest and most successful description of the physical world at fundamental scales. And its central claim is radical. In quantum field theory, the universe is not made of particles. It is made of fields, a field for each type of particle, filling all of space, always present, even in the deepest vacuum. The electromagnetic field is one of these. The electron field is another. There are quark fields, a gluon field, a Higgs field, neutrino fields. These are not mathematical tools used to calculate how particles interact. They are the fundamental constituents of reality. The particles we detect in experiments, photons, electrons, quarks, are not independent objects that exist in these fields the way fish exist in water. They are disturbances in the fields. They are what happens when a field is excited above its ground state. They are field events. When an atom emits a photon, it is not that a tiny particle was sitting inside the atom waiting to be released. The electromagnetic field in that region gets excited. A quantum of energy appears in the field. The photon comes into existence. When that photon is later absorbed by your eye, the field returns to a lower energy state at that location. The quantum of energy disappears. The photon ceases to exist. Creation and annihilation are not dramatic or unusual. They are the routine behavior of quantum fields, happening countless quintillions of times per second throughout the universe, in every atom, in every reaction, in every interaction between charged particles. The universe is not a collection of permanent objects. It is a network of fields that spend their existence creating and destroying excitations, trading energy, shifting between states, in an endless dance that makes up everything that has ever happened or will ever happen. In this picture, every photon in the universe, from the photon emitted in a nuclear transition in the core of a distant star to the photon bouncing off the page you are reading, is an excitation of the same single electromagnetic field. There is one electromagnetic field. It fills the universe. Every photon is simply a different local excitation of that one field. This is why all photons of the same frequency are absolutely identical. Not nearly identical in the way two manufactured products are nearly identical, with microscopic differences between them. Absolutely, fundamentally, perfectly identical. There is no deeper substrate that could make one red photon different from another red photon of the same frequency and polarization. They are both the same quantum state of the same universal field. There is no meaningful sense in which they can be labeled, tracked, or distinguished. This indistinguishability is not a limitation of our measurement tools. It is not that we have failed to find the property that distinguishes them. The property does not exist because the distinction does not exist. They are the same event in the same field. Now we arrive at the mystery that sits at the heart of this whole story. The mystery of why the photon never stops moving. An electron can sit still. A proton can be brought to rest. Even a neutrino interacting so weakly with the rest of matter that it passes through the entire Earth without stopping is a massive particle that, in principle, has a rest frame. But a photon is different. From the instant the electromagnetic field is excited, from the very first moment of a photon's existence, it is moving at 299,792,458 meters per second, the speed of light in vacuum, and it will continue moving at precisely that speed until the moment it is absorbed. Not approximately that speed, not that speed on average, exactly that speed. Always, under every possible circumstance, in every possible context, in every corner of the universe. There are no exceptions. There is no mechanism by which a photon can be slowed, stopped, or turned around. Why? The answer comes from relativity, but not relativity understood as an abstract theory about fast-moving objects. It comes from relativity understood as a revelation about the geometric structure of the universe itself, a structure in which space and time are not separate independent dimensions, but are woven together into a unified four-dimensional fabric whose properties have deep and inescapable consequences for every particle that exists within it. Einstein's special theory of relativity rests on a recognition that the speed of light is not simply a large number. It is a fundamental constant of space-time, a constant that encodes the relationship between space and time, the way the conversion factor between feet and meters encodes the relationship between two different ways of measuring the same distance. If you write down the geometry of space-time with full mathematical precision, the speed of light appears not as the speed at which light happens to travel, but as the conversion factor between spatial and temporal coordinates. It is woven into the geometric metric of the universe. It is, in a deep sense, not a speed at all, but a geometric ratio. The ratio between one unit of time and the equivalent amount of space. Given this geometric role, the speed of light is not something that could be chosen differently. It is not a parameter that God dialed in at the beginning of time, and could just as well have dialed differently. It is the signature of space-time's structure. Change the speed of light, and you would not have the same universe running a little differently. You would have a fundamentally different universe with a different geometric structure at its core. Every atom, every force, every relationship between energy and mass would change, because all of these things are built from the structure of space-time itself. Now consider what it means for a particle to move. Any particle, massive or massless, moves through space-time, not through space alone, but through the four-dimensional geometric continuum of space and time together. The way a particle moves through space-time is described by something called its world line, the path it traces through the four dimensions. For a massive particle standing still in space, the world line is a straight vertical line in time. The particle is not going anywhere in space, but it is still moving through time. For a massive particle moving through space, the world line tilts. In the geometry of space-time, the geometry that special relativity reveals, the maximum tilt a world line can have is exactly 45 degrees, and this maximum corresponds to motion at the speed of light. World lines more tilted than 45 degrees would correspond to superluminal motion, which would violate causality. The geometry of space-time makes these impossible. All world lines must be tilted at 45 degrees or less. For massive particles, the world lines can be anywhere up to, but not including 45 degrees. For massless particles, the world line must be exactly at 45 degrees. There is no other option. Now consider what mass means in the context of this geometry. Mass is not just a measure of how heavy something is. In relativity, mass is the parameter that determines how a particle's energy and momentum relate to each other and to its velocity. Einstein's full energy-momentum relation, not the simplified E equals mc squared that everyone knows, but the complete equation, states that the square of the total energy equals the square of the momentum times the square of the speed of light, plus the square of the rest, mass times the speed of light raised to the fourth power. For a massive particle at rest, the momentum term vanishes, and you are left with the famous rest energy. E equals mc squared. This rest energy is the energy a massive particle has simply by virtue of existing with mass, without any motion at all. It is the energy of pure being for a massive thing. For a massless particle, the rest mass term vanishes entirely from the equation. The result is that the total energy equals the magnitude of the momentum times the speed of light. Energy and momentum are directly proportional, locked together absolutely, with no possibility of having one without the other. If a massless particle has zero momentum, it has zero energy. But a particle with zero energy is not a particle. It is nothing. It does not exist. Therefore, a massless particle cannot have zero momentum. It must be moving. It must always have momentum. And because of the relationship E equals PEC, combined with the geometric structure of space-time, it must be moving at exactly the speed of light. Not as a speed limit it is trying to respect. Not as a goal it is reaching toward. As the only mathematically consistent motion available to it. A massive particle can be brought to rest because being at rest with mass still corresponds to a real physical state. A world line pointing straight through time, carrying rest energy. You can match velocities with a massive particle, accelerate to move alongside it, and in your reference frame, the particle is stationary. The concept of the particle standing still is coherent and physically realizable. For a massless particle, there is no such coherent state. You cannot match velocities with a photon. No matter how fast you accelerate, the photon continues to recede from you at the speed of light. Not because you are not fast enough, because the very attempt to construct a reference frame moving at the speed of light produces mathematical breakdown, the Lorentz transformations, which describe how different reference frames relate to each other, produce undefined results at light speed. Time dilation becomes infinite, length contraction becomes total. The reference frame itself ceases to exist as a mathematical object. There is no frame of reference moving at the speed of light, which means there is no rest frame for the photon, which means the photon has no rest. This is not a speed limit the photon bumps against like a car hitting its maximum engine speed. It is a categorical ontological fact. The photon does not slow down and stop because slowing down and stopping is not a state that exists for something with zero rest mass. Asking a photon to stand still is asking reality to accommodate a mathematical contradiction. The universe declines. People sometimes push this line of reasoning to a conclusion that sounds profound, but is actually technically meaningless. They ask what the universe looks like from the photon's perspective. If time dilation increases without limit as you approach light speed, then at light speed, does time freeze entirely? Does the photon experience its birth and its absorption as simultaneous events? Does all of space collapse to a point along the direction of travel? These questions have a seductive philosophical feel, but they are built on a faulty premise. The concept of a perspective requires a reference frame, a consistent set of coordinates from which measurements can be made. As just discussed, a reference frame at light speed does not exist. The mathematics produces infinities and undefined quantities. The photon does not experience time at all, not because time is frozen for it, but because experience requires a reference frame and the photon has none. Asking what the photon experiences is like asking what a number smells like. The question is syntactically coherent but physically empty. There is no answer, not because the answer is unknown, but because the question contains a hidden assumption that does not hold. Now let us consider the photon's momentum, which deserves its own moment of focus because it is genuinely extraordinary. Momentum, in the everyday world, is mass times velocity. A bowling ball has momentum because it is heavy and moving. A stationary object has no momentum because it is not moving. Momentum seems inextricably tied to mass, yet a photon has zero mass and still carries momentum. Not a tiny amount, a real, measurable amount that has real physical effects on real material objects. The resolution lies in Einstein's more general equation. For a massless particle moving at the speed of light, momentum is not mass times velocity. Momentum is energy divided by the speed of light. This is the whole relationship. A photon with energy E carries momentum E divided by c. Its energy comes from the frequency of the electromagnetic oscillation, so its momentum also comes directly from the frequency. Higher frequency means more energy, means more momentum. A gamma-ray photon carries vastly more momentum than a microwave photon. This is not an abstract statement. You can feel the consequences. Solar radiation exerts pressure on the surfaces it strikes, a tiny force produced by photons transferring their momentum to atoms on impact. For human-scale objects, this force is negligible compared to gravity. But for small objects in space, cut free from the dominance of gravity, the force is real and significant. Engineers have seriously considered using solar radiation pressure to propel spacecraft using enormous reflective sails, literally sailing between planets on the momentum of sunlight, with no propellant required, no chemical fuel, no engine. The photon's momentum is not a theoretical curiosity. It is an engineering resource. The same momentum principle means that photons can push electrons. When an atom absorbs a photon and re-emits it, the atom recoils, because each photon carries momentum, and conservation of momentum demands that the atom change its motion when the photon's momentum changes direction. Laser cooling, which is the technique that allows physicists to chill atoms to temperatures within a billionth of a degree of absolute zero, works by bombarding atoms with photons from carefully chosen directions so that the momentum kicks systematically slow the atoms down. At those extreme temperatures, the thermal motion of atoms becomes so slow that quantum mechanical effects dominate. Bose-Einstein condensates, states of matter that have no classical analog, where thousands of atoms melt into a single collective quantum state, are created this way. All of it, from the initial photon emission to the final exotic quantum state, flows from the fact that a massless particle can still carry momentum. The photon's polarization is another property that points toward the deeper structure of the field. Polarization describes the direction in which the electromagnetic field oscillates as the photon propagates. Because the oscillation involves electric and magnetic components that are perpendicular to each other and to the direction of travel, the photon's oscillation sweeps out a direction in the plane transverse to its motion. This direction is the polarization. It can be linear. The field oscillates back and forth along a fixed line. It can be circular. The field rotates continuously as the photon travels, sweeping out a helix through space. Or it can be elliptical, some combination. In classical electromagnetic theory, polarization varies continuously. You can rotate the polarization angle through any value from 0 to 360 degrees. But individual photons, because they are quantum objects, behave differently when measured. When you pass a single photon through a polarizing filter, the outcome is binary. The photon either passes or it does not. A photon that was diagonally polarized, hitting a vertical polarizing filter, does not emerge at half intensity. It either passes through completely or is stopped entirely, with the probability of each outcome depending on the angle between the photon's polarization and the filter's orientation. This is the quantum in action, the discreteness of outcomes that has no classical parallel and that shocked physicists when it was first encountered. Connected to polarization is the photon's spin, which is one of its most deeply quantum properties. Spin is a form of intrinsic angular momentum that particles carry, a quantum property with no classical equivalent, even though the word spin evokes rotation. The photon has a spin of 1 in units of the fundamental quantum of angular momentum. Because the photon is massless, its spin can only be oriented along or against its direction of travel. There is no state in which the spin points sideways relative to the direction of motion, a mathematical consequence of the photon's masslessness that emerges from the deep structure of relativistic quantum field theory. These two spin states correspond to the two circular polarization states, left-handed and right-handed. The polarization of light that you observe in everyday optics is the macroscopic manifestation of the spin states of individual photons. This brings us to one of the most important roles the photon plays in physics, a role that transcends its identity as the particle of light and places it at the center of one of the 4 fundamental forces of nature. The photon is the carrier of the electromagnetic force. In quantum field theory, forces between particles do not arise from invisible fields pushing and pulling at a distance in the way Newton imagined gravity. Forces arise from the exchange of particles, the gauge bosons, the messenger particles of each force, The strong nuclear force is carried by gluons. The weak nuclear force is carried by the W and Z bosons. Gravity, if it can be quantized, would be carried by gravitons. The electromagnetic force, the force that holds electrons in orbit around nuclei, that drives chemical reactions, that makes solid objects solid, that connects magnets and generates electricity, is carried by photons. When two electrons approach each other and repel, what is actually happening at the quantum level is that one electron emits a photon and the other absorbs it, with the exchange transferring momentum between them in a way that pushes them apart. This is the quantum description of the electromagnetic repulsion. The photons involved in this interaction are not the photons of visible light. They are what physicists call virtual photons, excitations of the electromagnetic field that exist only during the brief interval of interaction that cannot be directly detected as independent particles because they do not travel freely through space. They are the currency of force, the quanta by which charged particles negotiate their interactions through the electromagnetic field. The concept of virtual particles is subtle and easy to misunderstand. They are not particles that are somehow imperfectly real or particles caught in the act of materializing. They are a feature of the mathematical structure of quantum field theory, internal lines in the Feynman diagrams that describe interactions, representing field fluctuations that contribute to the outcome of physical processes without being detectable in isolation. The distinction between real and virtual photons is a distinction of role. Real photons propagate freely through space, carry energy over macroscopic distances, and can be detected by a detector. Virtual photons mediate interactions, exist only as intermediate states in a quantum process, and cannot be detected independently. Both are excitations of the same electromagnetic field, described by the same fundamental theory, just playing different parts. The theory that describes all of this with mathematical precision is called quantum electrodynamics, or QED. Developed in the late 1940s through the work of Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, QED is by almost any measure the most accurately verified theory in the history of science. Its crown jewel is the prediction of the anomalous magnetic moment of the electron, a correction to the electron's magnetic properties caused by the constant emission and reabsorption of virtual photons that the electron performs as it moves through the electromagnetic field. QED predicts this correction to more than 10 significant digits. Experimental measurement agrees with the prediction to better than 1 part in a trillion. This is a degree of correspondence so tight that if you predicted the distance from one side of the continental United States to the other with the same accuracy, your prediction would be off by less than the diameter of a human hair. No other scientific theory has achieved remotely comparable precision. The photon, in QED, is doing exactly what it is supposed to do. The reason the photon can serve as the carrier of the electromagnetic force, the reason it can be massless while the W and Z bosons that carry the weak force are enormously heavy, lies in the mathematical structure of the underlying field theory. The electromagnetic field possesses a special mathematical property called gauge symmetry. Without going into the full mathematical details, a gauge symmetry is a type of symmetry that the laws of physics maintain under a specific kind of transformation. The electromagnetic field's gauge symmetry is particularly elegant and particularly powerful. It is exactly this symmetry that protects the photon from acquiring mass. Mass, in the Standard Model, is typically acquired through the Higgs mechanism, a process whereby particles interact with the Higgs field that permeates space and thereby gain inertia. The strength of a particle's interaction with the Higgs field determines how much mass it acquires. Quarks interact strongly and have significant mass. Electrons interact less strongly and have less mass. Neutrinos interact very weakly and have tiny but non-zero masses. The W and Z bosons interact with the Higgs field through a process that breaks the symmetry of the weak force, giving them very large masses, roughly 80 and 91 times the mass of the proton respectively. But the photon does not interact with the Higgs field in the symmetry-breaking way. The electromagnetic gauge symmetry is not broken by the Higgs mechanism, it is preserved. And because the gauge symmetry is preserved, the photon remains massless. This is not an accident or a fine-tuning. It is a direct consequence of the mathematical structure of the Standard Model, the framework that has been tested against experiment after experiment for the past half-century and has yet to be caught in a significant error. The photon's masslessness is protected by mathematical necessity. As long as electromagnetism has gauge symmetry, and every experiment we have ever performed is consistent with it having gauge symmetry, the photon has zero mass. The experimental constraints on the photon's mass are extraordinary. Astrophysical observations of the behavior of magnetic fields in galaxies and the dispersion of pulsar signals at different frequencies have established that the photon mass, if it is not exactly zero, must be smaller than about 10 to the minus 54 kilograms. This is roughly 10 billion trillion times smaller than the electron mass, which is itself tiny. Every measurement is consistent with exactly zero. The photon is massless. Masslessness demands light speed. The photon moves at light speed. Every link in the chain holds. It is worth pausing here to reflect on what makes this chain of reasoning so remarkable. The photon's compulsory motion at light speed is not some arbitrary feature of light. It is a logical consequence that flows from the structure of the electromagnetic field, from the relationship between mass and energy in special relativity, from the geometry of spacetime itself. The universe is structured so that massless excitations of quantum fields move at a speed that is built into spacetime's geometry. The electromagnetic field is structured so that its fundamental quantum excitation is massless. These two facts together make the photon's perpetual motion not a mystery, but an inevitability, a logical conclusion from the deepest principles of physics, as inevitable as the conclusion that a triangle has three sides. Now, there is one more piece of this story that needs to be told because it is one of the most commonly misunderstood facts about light. When you look through a glass window, light appears to be passing through effortlessly. When you watch the sun set, its light has passed through miles of atmosphere. In optical fibers, light carries data around the world at, well, not quite the speed of light in vacuum, but close. The speed of light in glass is roughly 200,000 kilometers per second. In water, about 225,000. In diamond, around 124,000. Measured in these materials, light is slower than 299,792 kilometers per second. Does this mean the photons are slowing down? Does this violate the principle that massless particles must travel at light speed? No. What is actually happening is subtle, fascinating, and completely consistent with everything that has been said. When an electromagnetic wave enters glass, the oscillating electric and magnetic fields interact with the electrons bound in the atoms of the glass. These electrons are held in place by their atomic bonds, but can be driven to oscillate by the passing electromagnetic field. When charged particles oscillate, they themselves emit electromagnetic radiation. The result is that the original incoming photons and the radiation produced by the oscillating atomic electrons combine, overlap, and interfere. This combined electromagnetic disturbance, the superposition of the original wave and the waves generated by billions of oscillating electrons, propagates through the material at a reduced effective speed. This reduced speed is the speed of light in the material, and it depends on how strongly the material's electrons respond to the electromagnetic oscillation. But this is a collective, emergent, macroscopic phenomenon. At the level of individual quantum events, every photon-electron interaction occurs at light speed. Every photon traveling between atoms travels at exactly 299,792 kilometers per second. The apparent slowing is not any individual photon moving slowly. It is the result of a complex interference pattern between the original wave and all the waves generated by the atoms it has excited along the way. The photon itself, the quantum of electromagnetic field excitation, has never violated its massless nature. It is the medium responding to the field that creates the appearance of slower light. Strip away the material, and the light snaps back to full speed the moment it exits. This principle has remarkable technological consequences. The way different frequencies of light travel at different speeds in materials, the dispersion relation, means that a prism can separate white light into its component colors, each color being bent by a slightly different amount as it enters and exits the glass. The same principle governs the chromatic aberration that lens designers spend their careers correcting. It is why fiber optic cables must be carefully engineered to minimize dispersion, so that short pulses of data do not spread out as they travel. And it is why astronomers can infer the composition of distant gas clouds by studying which frequencies of light are absorbed as the light passes through them on its way to Earth. The photon is also responsible, through quantum electrodynamics, for the existence of chemistry, and therefore for the existence of everything living. The reason atoms form molecules is that electrons, when they are shared between atomic nuclei, experience electromagnetic interactions that create binding energy. The covalent bond between the two hydrogen atoms in a hydrogen molecule, the polar bonds in a water molecule, the complex scaffolding of carbon bonds that makes organic chemistry the basis of life. All of it is the electromagnetic force in action, mediated by virtual photons exchanged between electrons and nuclei. The electrons in a chemical bond are in quantum states shaped entirely by the electromagnetic force, and the stability of those states is what makes molecules stable, which is what makes atoms stay together, which is what makes matter solid, which is what makes the ground under your feet feel solid instead of simply dissipating into a cloud of dust. Every solid surface that has ever supported any living thing owes its solidity to this. When you press your hand against a wall, the reason you do not pass through it is not that some impenetrable substance is blocking you. It is that the electrons in your hand and the electrons in the wall repel each other through photon exchange. The electromagnetic force, carried by photons, is the force that makes matter behave as if it has surfaces. The photon is not just something to see by, it is something to exist by. Vision itself is a photon story. Photons from some source, the sun, a lamp, a glowing screen, strike an object. Some are absorbed, their energy converted to heat. Others are reflected, their direction changed. And some of these reflected photons travel in the direction of your eye. They enter through the lens, which focuses them. By exploiting the different speeds of different frequencies in glass, exactly the mechanism described above, onto the retina. In the retina, specialized photoreceptor cells contain molecules called opsins. These molecules, when struck by a photon of the right frequency, undergo a rapid structural change. A portion of the molecule, called retinal, snaps from one geometric configuration to another in less than 200 femtoseconds, 200 millionths of a billionth of a second, as it absorbs the photon's energy. This structural change triggers a cascade of chemical signals that travel along the optic nerve to the visual cortex. The photon has been absorbed, destroyed, its energy converted into chemistry, but the information it carried, the direction it came from, the frequency that determined its color, has been transduced into neural signals that your brain interprets as the image of the world. Every image you have ever seen is the result of photons being created, traveling, and being destroyed. Every color you have ever perceived corresponds to a frequency of electromagnetic field oscillation. The depth and richness of the visual world, the blue of the sky, the green of a forest, the red of fire, the silver of starlight, is the universe's electromagnetic field vibrating at different frequencies, and your brain translating those vibrations into the inner experience of color. The sky is blue for a reason that is itself a photon story. When sunlight enters the atmosphere, photons scatter off the nitrogen and oxygen molecules in the air. Shorter wavelength photons, the blue and violet end of the spectrum, scatter far more readily than longer wavelength red photons. The blue photons scatter in all directions, filling the sky with blue light that arrives at your eye from every direction. The red photons mostly pass straight through, which is why sunsets are red. When the sun is near the horizon, its light travels through much more atmosphere before reaching you, and by the time it arrives, almost all the blue has been scattered away, leaving the lower frequency reds and oranges. Photosynthesis is the universe's most extraordinary photon story. For roughly 3.5 billion years, a continuous process has been running on this planet in which photons from the sun enter chlorophyll molecules in plant cells and drive a sequence of chemical reactions that convert carbon dioxide and water into glucose and oxygen. The photon's energy, absorbed by the chlorophyll, is used to split water molecules, driving electrons into high-energy states from which they are passed through a chain of molecular machines. At the end of the chain, the energy has been stored in chemical bonds, the carbon-hydrogen and carbon-oxygen bonds of organic molecules. The photon is gone. Its energy persists in the molecular structure of food, Every living thing on Earth runs on photon energy. The bacteria in the soil, the grass in the meadow, the deer that eats the grass, the wolf that catches the deer. At every step of every food chain, the energy being metabolized was originally delivered by a photon from the sun. When your muscles contract to lift your arm, when the neurons in your brain fire to generate thought, when your heart beats to pump blood, the energy driving these processes can be traced back through the food you ate and further back through the food chain to photons that arrived from 150 million kilometers away and were absorbed by a leaf. You are, in a very literal thermodynamic sense, a photon storage and processing system, and those photons themselves were born in the core of the sun. In the solar interior, where temperatures reach 15 million degrees and pressures exceed 250 billion atmospheres, hydrogen nuclei fuse to form helium, releasing energy in the process. But the photons produced in the core do not travel directly to the surface. The sun's interior is so dense that a photon can only travel a microscopic distance before being absorbed and re-emitted in a random new direction. The photon bounces, is absorbed, is re-emitted, bounces again, in a random walk so tortuous that the journey from the core to the surface takes, on average, something between 10,000 and 170,000 years. The photons that are warming your skin today began their journey before humans existed as a species. They have been diffusing outward through the sun's plasma all that time, being constantly absorbed and re-emitted, losing energy as they go, produced as gamma rays in the core, degraded to X-rays, then ultraviolet, then visible light by the time they reach the surface, before finally escaping into space and making the 8-minute journey to Earth. Stars are photon factories. Every star in the sky is a sphere of hot plasma, producing photons in its core and radiating them from its surface. The color of a star, blue-white for the hottest, red for the coolest, is a direct consequence of the temperature of its surface and the distribution of photon frequencies that temperature produces. Red giants, white dwarfs, neutron stars, exotic stellar remnants, each emits photons of a characteristic spectrum that carries information about the star's temperature, composition, velocity, and distance. Astronomers read the universe through its photons. Every observation made by every telescope ever built, every discovery about galaxies, quasars, nebulae, the cosmic microwave background, has been made by collecting and analyzing photons. The most ancient photons we can directly detect are the photons of the cosmic microwave background, the afterglow of the Big Bang. In the early universe, the plasma of particles was so hot and dense that photons could not travel more than a short distance before being absorbed and re-emitted. The universe was opaque. Then, when the universe was about 380,000 years old, it cooled enough for electrons to combine with protons to form neutral hydrogen atoms. With the electrons locked up in atoms, the photons were suddenly free. The universe became transparent. Those photons that were released at that moment have been traveling ever since, for over 13 billion years, gradually losing energy as the universe expanded and stretched their wavelengths. They arrive today as microwaves, a faint, extraordinarily uniform glow from every direction in the sky, the oldest light we can detect, a fossil record of the universe's first transparency. The tiny variations in that glow, temperature fluctuations of about 1 part in 100,000, are the seeds of all the structure we see today. Galaxies, galaxy clusters, the large-scale web of filaments and voids that makes up the cosmic structure, all of it grew from those tiny ripples in the oldest photons. To study these photons is to look directly at the early universe, to read the initial conditions of cosmic structure from the electromagnetic field as it was 13.8 billion years ago. Every advance in our understanding of cosmology has come from studying photons more carefully, with better instruments, at more frequencies. Radio astronomy revealed pulsars and quasars and the microwave background itself. X-ray astronomy revealed the hot gas in galaxy clusters and the accretion disks around black holes. Gamma-ray astronomy revealed the most energetic explosions in the universe. Infrared astronomy revealed the birthplaces of stars inside cold molecular clouds. Each window of the electromagnetic spectrum, opened by technological advance, has shown us a different face of the universe, a different population of objects invisible at other frequencies. The universe is not silent. It is saturated with electromagnetic field excitations of every frequency, from radio waves with wavelengths of kilometers to gamma rays with wavelengths smaller than atomic nuclei, carrying information about processes ranging from the gentle oscillation of electrons in planetary magnetospheres to the cataclysmic collapse of stellar cores. All of it, photons. All of it, the electromagnetic field vibrating with its fundamental quanta. And yet, for all the precision and completeness of quantum electrodynamics, for all the extraordinary agreement between theory and experiment, physicists know that the Standard Model is not the final word. It does not include gravity. It does not explain why the universe is made of matter rather than antimatter. It does not identify dark matter or dark energy, the dominant components of the universe's energy budget. It contains parameters, particle masses, mixing angles, coupling constants, that it takes as inputs rather than deriving from first principles. The Standard Model is an extraordinarily successful effective theory, a description that works with astonishing accuracy within its domain, but it is not the fundamental theory of everything. There is more to find. Some theoretical frameworks for going beyond the Standard Model suggest that the photon has additional structure at scales far smaller than anything we can currently probe. String theory, in its many variants, proposes that all particles, including the photon, are not point excitations of fields, but are instead the vibrational modes of tiny one-dimensional objects, strings of energy at the Planck scale, roughly 10 to the minus 35 meters. Different vibrational patterns of the string correspond to different particles. The photon would be one specific mode of string vibration. If this is correct, then the photon does have a kind of internal structure, not made of smaller particles, but made of a geometry of vibration. The question of what a photon is made of would have a new answer at a deeper level than the Standard Model currently probes. Other approaches, such as loop quantum gravity, propose that space-time itself is discrete at the Planck scale, that space and time are not smooth continua, but are built from indivisible quantum units of geometry. If this is correct, then the electromagnetic field that the photon is an excitation of does not live in a smooth, continuous space-time, but in a quantum geometric structure. The photon, as a disturbance in that field, would inherit properties of that quantum geometry. What it means to be a photon would shift again, deepened by a new understanding of the structure of space and time. These are open questions. They are frontiers. They are places where physics has not yet arrived, where the experimental evidence has not yet guided theory to a definitive answer. The story of the photon is not finished. It never was. Each time physicists thought they had understood light, when the Greeks settled on their theories of vision, when Newton proposed his corpuscles, when Young's experiment seemed to end the debate, when Maxwell unified electricity and magnetism and light, when Einstein revealed the quantum, there was always more beneath the surface, always a deeper level of structure waiting to be uncovered. What we know with confidence, what has survived every experimental test, what underpins the technology of the modern world, from the laser to the solar panel to the fiber optic network, is this. The photon is a quantum excitation of the electromagnetic field. It is the minimum possible unit of electromagnetic energy at a given frequency. It has zero rest mass, no internal structure, no spatial extent in the classical sense. Its energy and momentum are entirely determined by the frequency of the field oscillation. It travels at the speed of light because it has zero mass and because the speed of light is built into the geometric structure of space-time itself. It is created when charged particles accelerate or when quantum systems release energy, and it is destroyed when it transfers that energy to matter. It is the carrier of the electromagnetic force, the messenger particle of the most familiar force in everyday experience. It is the currency of vision, the engine of chemistry, the source of all biological energy, the messenger that carries information from distant stars across the universe to our telescopes and our eyes. The next time light falls on your face, whether it is the warmth of afternoon sun through a window, or the blue glow of a screen in the dark, or the first pale brightness of dawn, you are feeling the electromagnetic field vibrating. Quintillions of photons arriving every second, each one a quantum of that universal field, each one carrying a tiny indivisible packet of energy that was created somewhere, traveled through space at the only speed the universe permits, and is now being absorbed by your skin and eyes and the molecules of your body. They come from the sun, born in a nuclear furnace and diffusing outward through plasma for tens of thousands of years before making the final 8-minute dash across the void. They come from lamps, born from the acceleration of electrons in heated filaments or in the quantum transitions of excited gas atoms. They come from screens, born from the controlled emission of semiconductors driven by precisely tuned electronic signals. Each photon that reaches you is the same field that connects you to the farthest visible galaxy, to the first moment of cosmic transparency after the Big Bang, to every process in the universe that involves charged particles doing anything at all. You are bathed in the electromagnetic field's excitations. You have always been. Every photon you have ever seen, every quantum of light that has ever carried a signal to your eye and allowed your brain to reconstruct an image of the world. Every one of those photons was the electromagnetic field of the entire universe locally excited into its first quantum state. Before reaching that moment of absorption, before the photon's brief existence comes to its end, it is worth sitting for a moment with the strangeness of what has just been described. Not the strangeness of a parlor trick or a counterintuitive puzzle, but the strangeness of genuine revelation. The universe is not the way it looks, not even close. The hardness of a rock and the warmth of sunlight and the colors of a sunset are all expressions of the same underlying phenomenon. The electromagnetic field vibrating with its fundamental quanta, exchanging energy between atoms, carrying information from place to place, doing the quiet, infinite work of holding matter together and letting light travel. The photon is not a feature of the physical world. It is one of the structural foundations on which the physical world is built. To appreciate this more fully, consider the role of the photon in the technology that defines modern civilization. Every device that emits, detects, or manipulates light is a photon machine. The laser, one of the most transformative inventions of the 20th century, is a machine for producing vast numbers of photons in the same quantum state, with the same frequency, the same polarization, traveling in the same direction, with a fixed phase relationship to one another. This synchronized state of billions of photons is only possible because photons are bosons, particles with integer spin that can occupy identical quantum states without limit. Electrons cannot do this. The Pauli exclusion principle forbids any two electrons from occupying the same quantum state, but photons pile into the same state eagerly, even preferentially. When a photon of the right frequency passes through a medium with excited atoms, it does not just pass through, it stimulates those excited atoms to emit additional photons into exactly the same quantum state. One photon becomes two, then two become four, then four become eight. The cascade of stimulated emission produces an avalanche of photons all marching in perfect lockstep, an optical army of identical quanta. This is laser light, coherent, monochromatic, directional, and it is used today for everything from eye surgery and precision measurement to cutting steel, reading data from optical discs, and transmitting information through glass fibers at terabit per second rates. The solar panel is also fundamentally a photon machine. When sunlight strikes the surface of a semiconductor, such as silicon, photons with sufficient energy are absorbed by electrons in the material. Each absorbed photon promotes an electron from a low-energy state to a high-energy state, creating a free electron-hole pair. If the material is designed correctly, with a built-in electric field at a junction between two types of semiconductor, the promoted electrons are swept in one direction and the holes in the other. This separation of charge creates a voltage, and if the circuit is completed, a current flows. Sunlight has been converted directly to electricity. The photovoltaic effect, as it is called, is nothing more than the photoelectric effect that puzzled Hertz and that Einstein explained, applied at industrial scale with precisely engineered materials, generating the electrical power that is increasingly running the world. The camera sensor in every smartphone is a photon detector of extraordinary sensitivity. Each pixel in the sensor is essentially a tiny photovoltaic device. Photons arriving from the scene being photographed strike the pixel and liberate electrons. The number of electrons liberated is proportional to the number of photons that arrived, which is proportional to the brightness of the scene at that point. Different pixels, covered with different color filters, are sensitive to different frequency ranges of the spectrum. The camera reads out the electron counts from every pixel and reconstructs, from the statistics of photon arrivals, a digital representation of the original scene. Photography is applied quantum electrodynamics. Every image ever taken with a digital camera is a map of photon counts. Medical imaging extends this principle into realms of extraordinary practical consequence. X-ray imaging works because X-ray photons, high-frequency, high-energy electromagnetic quanta, pass through soft tissue but are absorbed or scattered by denser materials like bone. The differential absorption casts a shadow of the body's internal structure onto a detector. CT scanning uses the same principle but rotates the X-ray source around the patient and uses computational reconstruction to build a three-dimensional image. MRI, magnetic resonance imaging, works with a completely different principle, but still ultimately involves photons. Radio frequency electromagnetic pulses excite the quantum spin states of hydrogen nuclei in the body, and the return signal, as those spins relax back, is detected as radio photons, mapped to produce detailed three-dimensional images of soft tissue that X-rays cannot reveal. PET scanning, positron emission tomography, uses the photons produced when a positron, the antimatter twin of the electron, annihilates with an electron inside the body, producing two gamma-ray photons flying in exactly opposite directions. By detecting both photons in coincidence, the scanner can pinpoint the location of the annihilation with great precision. Every one of these medical technologies is, at its root, a photon story. The global information infrastructure depends on photons in a way that has become so natural that most people have forgotten it is remarkable. Optical fiber cables, bundled in their thousands under oceans and across continents, carry information as pulses of light, sequences of photons being turned on and off to encode bits of data. A single optical fiber, thinner than a human hair, can carry hundreds of terabits of data per second by using multiple frequencies of light simultaneously, each frequency carrying an independent stream of information, all traveling together through the same strand of glass, separated at the receiving end by their frequency differences. The entire internet, all of the video, voice, data, and communication that flows between continents, rides on photons moving through glass at close to the speed of light, guided by the principle of total internal reflection, trapped inside the fiber by the same refractive properties of glass that slow light down to 2/3 of its vacuum speed. None of this would be possible without the photon's dual nature as both the quantum of electromagnetic radiation and the carrier of the electromagnetic force. The absorption and emission of photons by atoms and electrons in semiconductors that make solar panels and cameras work, the propagation of coherent photon states that makes lasers work, the refraction that makes lenses and optical fibers work. All of it is the electromagnetic field doing its fundamental work, mediated by its fundamental quantum excitations. There is a question that sits underneath all of this technological wonder, and that does not often get asked clearly enough. Why is the electromagnetic force the one that underlies all of this? Why not the strong force or the weak force? The answer lies in a combination of the photon's masslessness and the long range of the electromagnetic force. The strong force, mediated by massless gluons, would seem to be a candidate for a long-range force, but gluons carry a property called color charge, a type of charge analogous to electric charge but with 3 varieties rather than 2. And because gluons themselves carry color charge, they interact with each other in ways that cause the strong force to behave entirely differently from electromagnetism at large distances. Instead of getting weaker as distance increases, the strong force between quarks gets stronger, trapping quarks permanently inside protons and neutrons and preventing free quarks from existing in isolation. Gluons, despite being massless, are never observed as free particles. The strong force operates only at the scale of atomic nuclei, roughly a femtometer. The weak force is carried by the massive W and Z bosons. Because they are heavy, acquiring their mass through the Higgs mechanism, the weak force is short-range, operating only over distances far smaller than a proton. It is relevant to radioactive decay and to the nuclear reactions that power stars, but it has no presence at the scales where chemistry, biology, and ordinary matter operate. The electromagnetic force, by contrast, carried by the massless photon, obeys an inverse square law that falls off gently with distance but never goes to zero. An electron can feel the electromagnetic field of a proton across an entire atom, across a molecule, across a crystal lattice. The electromagnetic force is why atoms have the size they have, why molecules form, why metals conduct electricity, why insulators insulate, why magnets attract, why generators generate and motors rotate. It operates across all scales from subatomic to macroscopic. It is the force of everyday life in a way that the strong and weak forces are not. And this is entirely because the photon is massless and the electromagnetic force is long-range. The gravitational force, also apparently long-range, is familiar at large scales but negligibly weak at atomic scales. A trillion times weaker than electromagnetism at the scale of 2 electrons. Gravity shapes planets and stars and galaxies because it is always attractive and cumulative. Every bit of mass in a large object contributes to its gravitational pull, but it plays no role in atomic physics, chemistry, or biology. The photon's masslessness, the geometric protection of the electromagnetic gauge symmetry, the resulting long-range nature of the electromagnetic force, these are what make the photon the governing particle of everyday physical reality. It is also worth dwelling on what the photon tells us about the nature of empty space. The intuitive picture of vacuum, of empty space, is of nothing. Pure absence. A void in which there are no particles, no fields, no properties of any kind. But quantum field theory destroys this picture completely. The vacuum is not nothing. It is the ground state of all the quantum fields that fill space-time. Even in the deepest possible vacuum, with no photons, no electrons, no quarks, no particles of any kind, the electromagnetic field is still there. The electron field is still there. Every quantum field is still there, vibrating with quantum uncertainty at its lowest possible energy level. The vacuum is not empty. It is full of fields in their quietest possible state, fluctuating with the minimum quantum noise that the uncertainty principle demands. These vacuum fluctuations have real physical consequences. One of the most famous is the Casimir effect. If you place 2 flat conducting metal plates very close together in a vacuum, separating them by a distance of a few nanometers, a tiny attractive force appears between them. This force is not electrostatic. It is not magnetic. It arises because the conducting plates constrain which modes of the electromagnetic field can exist in the narrow gap between them. Wavelengths longer than twice the gap cannot fit between the plates, so those modes are suppressed inside the gap. Outside the plates, all modes are permitted. The result is that there is slightly less vacuum energy between the plates than outside, and this energy difference produces a pressure that pushes the plates together. The Casimir effect is the force of the vacuum itself, of the electromagnetic field fluctuating in its ground state, pressing on conducting surfaces from the outside. It has been measured experimentally, and the measurements match the quantum field theory prediction. The vacuum pushes back. Another consequence of vacuum fluctuations is the Lamb shift, a tiny but precisely measurable displacement of certain atomic energy levels from the values that a simpler quantum mechanics would predict. The displacement arises because the electron in a hydrogen atom is not sitting in a static electromagnetic field. It is surrounded by a fluctuating vacuum, constantly being jostled by the random appearance and disappearance of virtual photons in the electromagnetic field's ground state. These fluctuations shift the electron's energy levels by a small but definite amount, and the shift was first measured by Willis Lamb in 1947. Explaining the Lamb shift was one of the motivating challenges that drove the development of quantum electrodynamics. QED explains it correctly. The vacuum fluctuations are real. The vacuum energy of quantum fields also underpins one of the deepest unsolved problems in physics, the cosmological constant problem. According to quantum field theory, the vacuum should have an energy density arising from the ground state fluctuations of all the fields in nature. When you try to calculate this energy density, you get an enormous number, far larger than any observed properties of the universe can accommodate. The observed cosmological constant, which describes the energy density of empty space and which drives the accelerating expansion of the universe discovered in 1998, is about 120 orders of magnitude smaller than the naive quantum field theory prediction. This discrepancy, 120 powers of 10, is the largest gap between a theoretical prediction and an observed value in all of science. No one knows how to close it. Something is canceling the vacuum energy with extraordinary precision, but we do not know what or why. This is one of the deepest unsolved problems in theoretical physics, and the photon, as the quantum of the electromagnetic field, is part of the contributing vacuum energy that makes the problem so acute. These open frontiers are not embarrassments, they are invitations. Every great physical theory in history has had boundaries, regions where it worked perfectly and regions where it failed or left questions unanswered. Newtonian mechanics worked magnificently for cannonballs and planets, but failed for particles near the speed of light. Maxwell's equations described electromagnetic waves beautifully, but could not explain atomic spectra or the photoelectric effect. The standard model of particle physics is a triumph of human understanding, but it cannot explain gravity, dark matter, dark energy, or the cosmological constant problem. The incompleteness is not a failure. It is a map of where the next revolution in understanding will come from. The history of physics is a history of confronting the inadequacy of inherited pictures and replacing them with something stranger, deeper, and more beautiful. Every time physicists thought the universe was finally understood, that its fundamental constituents had been identified and its governing laws written down, reality surprised them by being more subtle. The discovery that light came in quanta was precisely such a surprise. The discovery that particles were field excitations was another. The discovery that empty space has energy, that the vacuum is alive with fluctuations, that space-time itself may be discrete at the Planck scale. These are the kinds of surprises that drive physics forward and that keep the story of the photon, like all the deepest stories in physics, permanently unfinished. What the photon has taught us, most fundamentally, is that the world is stranger and richer than it appears, that the things we take for granted, the solidity of objects, the warmth of sunlight, the colors of the sky, rest on a foundation so exotic and so counterintuitive that grasping it requires abandoning almost everything that ordinary experience teaches us about the nature of reality. Fields, not particles, quanta, not waves, geometry, not forces, masslessness demanding motion, the speed of light built into the structure of space-time, the vacuum seething with energy. The photon, in all of its massless, restless, structureless immediacy, is a window into all of this, into the true character of a universe that is, at its deepest level, nothing like what it looks like from the surface. It moved at the only speed it was ever allowed to move. It carried the only energy its frequency permitted. It came from some source and ended in your eye, or your skin, or the leaf of a plant, or the pixel of a camera. It was born and it died. In between those two events, it was one of the most fundamental, most elementary, most irreducible things in existence. A single quantum of one of the four forces that hold the universe together. A ripple in the field that fills all of space. The particle of light, the messenger of electromagnetism. The thing that has no size, no mass, no rest, no stillness, no interior, no past older than its creation, and no future beyond its absorption. That is the honest answer to the question that sounds so simple. What is a photon? It is not a tiny glowing ball. It is not a miniature bullet. It is not something made of smaller things. It is the electromagnetic field in its minimum state of excitation, the smallest possible disturbance at a given frequency that the universe's electromagnetic fabric can sustain. Everything else you need to know about a photon follows from that single description, by strict logical and mathematical necessity, with no room for exceptions. And yet the description, though accurate and complete by the standards of current physics, does not feel like an ending. It feels like a beginning. Because the electromagnetic field, whose excitations we call photons, is not the only quantum field. It is one of many, and they are all there, always, in every corner of the universe, vibrating with their ground state quantum noise. The story of the photon is an invitation into the story of fields, and that story, the story of what the universe is fundamentally made of, is still being written. A photon, what the universe does when it wants to move energy and information at the maximum speed that geometry allows. And there is nothing in all of physics more fundamental, more pervasive, or more quietly astonishing than that. Every time you open your eyes, the universe is answering the question with trillions of simultaneous examples, arriving at the speed that space-time permits, carrying the energy that frequency demands, disappearing into the molecules of your retina so that you might, for a moment, see. The photon asks nothing of you. It does not slow down for observation. It does not pause to be admired. It travels, absorbs, ceases. It is, in its brief and absolute existence, the simplest and the most complete expression of what the universe is doing at every moment, converting potential into motion, field into quanta, energy into information, darkness into light. No other particle captures the essence of quantum field theory quite so nakedly. No other fundamental entity is quite so stripped of the familiar props of mass and rest and interior structure. The photon is, in a sense, the universe at its most honest, showing you exactly what it is made of, if only you know how to look.